Hey, what's up, everybody? We're taking a look at the second part of our Unit 2 reciprocal and rational functions. For the remainder of this unit, we're going to focus on rational functions. So no longer will we be doing things like getting the reciprocal of the y coordinates and things like that, but you're going to see some similarities. All right, we are still doing reciprocal functions in a way, but for the remainder of this unit, we're going to focus more on sketching graphs rather than doing it point by point. We're going to take a look at using mapping notations to move things, to translate things to the left, to the right, to stretch, and to do reflections around the x and y axis, things of that nature. So we're going to be using mapping notations and all that sort of thing like you did in 12A earlier this semester. So that's what's up right about now. So I'm just going to show you a few introductory things. First of all, rational functions are any functions that have x's on top and bottom of a fraction is basically the way I can break that down for you, all right? So anytime you have an x on the denominator, and could be x's on the numerator as well. All right, if you see functions written in that form, then they are rational functions. Really what you're looking for is an x on the denominator in any type of form. So you haven't actually sketched any graphs like that yet in grade 11 or grade 12 until right about now. So what I have below is the basic graph, just y equals 1 over x. That's the most basic rational function, and every other function that we take a look at will be a transformation of that function. So when we're looking at how things have shifted to the left or to the right, up or down, or have been stretched or reflected, it is this basic graph that's in front of you that we are going to be reflecting. So notice here that this graph is pretty simple. It's broken up into two pieces. Looks a little familiar. Looks something like the reciprocal functions you've drawn. And notice that the horizontal and vertical asymptotes are just the x and y axis. And then we can write the domain and range for this as being all real numbers, but excluding the number of 0. So if you wish to, okay, you can rewrite these domains and ranges like this instead. Okay, you can say that x cannot equal 0. As we've already discovered, okay, sometimes it's easier for these just to state what x and y cannot equal to. I'll leave it up to you to decide that. And notice that we have two key points here. So these are the key points of the original function. So whenever we do a transformation function and we do a mapping notation, these are the 2 points that you're always going to put into the mapping rule. And just to show you on Desmos what this looks like, maybe a nicer graph, we have this sort of thing, okay? So this is the basic y is equal to 1 over x function. We have asymptotes along the x and y axis. And you can see right here that as x increases in value, 1 over x will get closer and closer to 0, but never actually touch. And then if you go into like the smaller x values, like 0.5, 0.1, and so on, you can see that as x is a smaller and smaller number, closer and closer to 0, 1 divided by an increasingly small number will give you a y value that's very large. Okay, so these go on to infinity, and you can see the asymptotes are along the x and y axis. And when we do translations, those asymptotes will move horizontally or vertically with